Hello everybody, welcome to my video. During the first video compare we compare the longitudinal frame and the transverse frame. Which one of these we're gonna solve for shear, and we found out the transverse frame has a greater shear than the longitudinal frame, and therefore when you have a greater shear, of course you will get a greater moment. The goal for a structural designer is to find the maximum moment of the structural frame. So transverse frame will produce that maximum moment compared to the longitudinal frame. Okay, we're going to be doing wind loads analysis using Portal method. The criteria is number one, the location. My location is Toronto, Ontario, Canada, and Canada has, or Ontario has, a maximum recorded velocity of 70 miles per hour, and the coefficient of wind velocity is 0.9. The location is wherever your location is, you can find out the maximum velocity in your area. My area is Toronto, Ontario, and has 70 miles per hour. Due to the velocity of the wind applied to the wall of your building, it produces a dynamic pressure. Wind velocity produces a dynamic pressure, PD. Dynamic pressure is given in relation as PD is equal to 1/2 times 1.2 kilogram per meter cube. That's the air. The air density at 20 degrees centigrade is 1.2 kilogram per cubic meter. PD is 1/2 times 1.2 kilogram per meter cube times velocity square. The velocity here is in meter per second, and the dynamic pressure is in Newton per meter square. And since I have 70 miles per hour, I have to convert that from miles per hour to kilometers per hour to meter per second. So let's convert that now. 70 miles per hour times, this is hour. In 1 hour there are 3,600 seconds, and in 1 mile there are 1.6 kilometer per 1 mile, and in 1 kilometer there are 1,000 meter per 1 kilometer. Kilometer cancel, miles cancel, hours cancel. The result of this is in meter per second. Okay, let's calculate that. Calculating now 70 times 1.6 times 1000 divided by 3600 equals to 31.11 meter per second. So the 70 miles per hour is actually 31.11 meter per second. Now since we have the meter per second as the velocity of the wind, the v squared there, we can now solve for the dynamic pressure. Dynamic pressure when applied to the wall, it becomes magnitude of a wind load. Okay, so PD is equal to 1/2 times 1.2 times 31.11 squared hat. PD now is equal to 31.11 times equals times 1.2 was divided by 2, 586.69. This is Newton per meter square. Now to change that to kilonewton, we need a kilonewton, right? Change that to kilonewton, you divide it by 1000. To divide 1000, you have to move the decimal point from the right to the left. 3 places from the right to the left. So 1, 2, 3. So therefore it is 0.581 kilonewton. That's 0.581 kilonewton per meter square. Now to find the load, find the wind load, now let's find the wind load. Wind load now. Wind load F1. Wind load F1 is equal to PD multiplied by the tributary area of F1. Okay. The tributary area of F1 is from here. Half of this, you draw a line. That's the tributary area of the column. And the point of application of the wind load is at the joint. The tributary area for that joint is half and half of both sides, below and above. This is the tributary area of F1 now. And this side here is 5 meters. So this is 2.5. And this is half is 3 here. 3 here, that's 6. So therefore the tributary area F1 is equal to 6 times tributary area for F1 is 6 times 2.5. 6 times 2.5 equals to 15. square meter. That is 15 square meter. So F1 now, your wind load one now is equal to the 0.581 kilonewton per meter square times 15 meter square, meter cancel, you get F1 now equal to 0.581 times 15 is equal to 8.72 kilonewton. Okay, the 8.72 kilonewton is F1 applied to the joint. All the wind loads are applied to the joint where the column and the beam are together. So this is 8.71 8.71 kilonewton. Now solve for F2. The second wind load is also PD. This is PD1, okay? This is 1, and now PD2 times tributary area of F2. Wind load number 2 is PD2 multiplied with the tributary area of F2. The tributary area of F2 is measured from the tributary area 1 all the way to the ground floor, because there's no more joint here. Okay, this is the ground floor already, so all the way to the ground floors. The tributary area for wind load number 2 is here, that there, all the way to the ground floor. Right, and that ground floor there is, the height of that is 6 meters. The height of first floor is 6 meters plus 2.5. 6 meter plus 2.5 is 8.5 times 6. So the tributary area for F2, tributary area for F2 is equal to 8.5 times 6 is equal to, this is 8.5 times 6, this is 8.5 from here all the way down to the ground floor, and that length there is 3 plus 3 equals 6. So let's solve for the tributary area number 2. That is 8.5 times 6 is equal to 51 square meter. Tributary area number 2 is 51 square meter. So F2 now is equal to the PD. PD is put it like 0.81, 0.581 times 51. That will give you times 0.581, give you a 29.63 kilonewton. Okay, so F2 is 29.63. So F2 is 29.63 kilonewton. Now for the next video, we'll be solving the shears for the transverse frame. Okay, so you have now the F2 and the F1, which is loaded there in the transverse frame. All the wind loads are applied at the joint where the column and beam frame together, and the tributary area is between half of this and half of that and half of this for the first tributary area, and the F2's tributary area, this is the joint, and since there's no more, this is the ground floor, this is the ground floor level, there's no more joint there, there's no basement, so therefore the tributary area for the second wind load is from here all the way down to ground floor. That's how you get 51 meters square. There we go, you have the F1 and F2. Next video is the